Okay, so while those keep trickling in, I think I'm just going to get started on the introduction about the organization that I work for and the work that we do. So this workshop is part of the Wetland Workshop series that DNDA puts on, and DNDA stands for Delridge Neighborhood Development Association. We are a small nonprofit in West Seattle that works on developing the underserved community of Delridge. It was historically redlined, and we do development through arts, nature, and housing. So we have affordable housing, and we work to bring arts and access to nature to low-income communities. And so part of our work, so I work for the nature team on our wetland project. We recently, a few years ago, bought an old substation from the city of Seattle and are restoring the land to be a functional wetland site. And so we have a whole series of these workshops, and this is part of them. And this workshop is part of like a two-part workshop series. Next month, we'll be looking at the future of restoration practices in a changing climate. Yeah, so if you have any questions about that, feel free to unmute and ask me or put it in the chat. So today we have Taryn Black joining us, and she is a glaciologist from the University of Washington working on her PhD, looking at glaciers. And yeah, I'm super happy to have her. And so just before I pass it over to her, we definitely encourage participation, but that can be a little bit tricky to handle on Zoom. So if you have a question, just go ahead. Everybody, I hope you know how to use the hand raise feature. It takes a little bit of trying. Everything with Zoom takes trying, right? And so I'm pretty sure if you go under participants and then click more, you can raise your hand. And if that's not right, then someone please tell me how to do it. Okay, and yeah, so I'll be also keeping an eye on the chat to make sure that all questions are getting answered. And so with that, I'll pass it over to Taryn, presenter.
Great, thank you so much, Bree. I'm gonna go ahead and share my slides here. Let's see. Okay. So like Bree said, I'm Taryn. I'm a grad student at the University of Washington, and I study glaciers, and I have a background in geology, and I'm from the area. So I'm going to talk about the geology and paleoecology of the Puget Sound today. And again, if you do have questions, feel free to pop those in the chat or raise your hand. I might not be able to see them if I'm looking at my slides, but I'll try and keep an eye on that, or feel free to unmute yourself, or Bree can alert me to those. So what if I told you that where I'm sitting today, where you're sitting today, if you're in Seattle or the Puget Sound, it used to be under 3,000 feet of ice? That is true. We used to have a very large ice sheet that covered part of the Puget Sound. And I'm going to talk about that today. I'm going to talk about some of the faulting in the area, landslides, all kinds of different processes that have shaped the region that we sit in now. So I'm going to share a bit about the regional geology of the Puget Sound, a bit about paleoecology, and also the geologic history of the region. So regional geology, I first want to give a bit of context about where the Puget Sound sits in the larger, in the state of Washington and also in the greater geologic area. So I really love this diagram. This is from Randall Monroe, who makes the XKCD webcomic, if you've heard of it. It's a very simple, he does this thing where he makes sketches using only the 10,000 most common words in the English language to describe complicated processes. And so what we have here is on the left, let me get my laser pointer here. We have two very large bodies of rock that are coming together. So these are what we call tectonic plates. These are just very, very large, kind of flat-ish things of rock on the surface of the Earth that kind of slowly move around. There's one over here that's under the Pacific Ocean. And there's another one over here that's part of North America. And they're coming together, and the piece that's the Pacific Ocean is going under the piece that's North America, and forming the Olympics and the Cascades, and also a little trough that we call Puget Sound. So this area is known as the Cascadia subduction zone. So that's what this process is called, is subduction, and where this happens is the subduction zone. This is why we have, I don't know, my slides keep advancing. This is why we have these big mountain ranges. That's why we have volcanoes in the Cascades, is as this big slab of rock is descending into the earth, it heats up the rock around it, and a little bit of that melts and comes up to the surface as volcanoes. And in between those two mountain ranges that get pushed up, you get a little bit of a basin. It's not always filled with water as we have in the Puget Sound. You can see this line here represents the length of the entire subduction zone, where it's called the Juan de Fuca tectonic plate is descending beneath the North American plate over here. And you can see like that subduction zone extends from up in BC all the way down offshore down to Oregon. And we don't have a big water trough like the Puget Sound in Oregon or in Northern California. The reason we have one in the Puget Sound is actually because of glaciers, and we'll come back to that later. But anyway, so the fact that we have this big active margin offshore means that we have a lot of active geology in the Pacific Northwest. Some of it's a bit more obvious, like, you know, the giant volcano that is looming over the city. Some of it takes a bit more guidance to see. So this is a professor at the University of Washington in the geology department who takes students on a lot of field trips. And he's just explaining a feature in some glacial deposits on Whidbey Island. And when I think about geology and the processes that shape our landscape and just trying to read the stories in those rocks, I really like to think of this quote from one of my professors. Her name is Jody Bourgeois. She was also a professor in the Earth and Space Sciences department at UW. She said that geology is comprised of long periods of boredom, punctuated by short periods of terror. This might sound familiar. It's a modification of a quote about war, I believe, from, I think it was from World War I or II. But in this case, our long periods of boredom are the times when not a whole lot is going on geologically. We've got maybe a river that's just carrying sediment, and it's slowly moving that sediment from one place to another, maybe slowly eroding some sediment away from the bottom or the sides of the stream and maybe dropping it somewhere else. But it's not, I mean, I love rivers, they're great, but it's not super exciting. But then there's the short periods of terror, and that's what in geology we call an event. It's something like a landslide, or an earthquake or a volcanic eruption, something that rapidly reshapes the landscape around it. So some examples of this that we might see around here include coastal bluffs, like these in Whidbey Island, which contain deposits from glaciers that were slowly laid down over hundreds and thousands of years. But those were all laid down flat, right? Like all of this sediment that was laid down here wasn't laid down as a bluff in the first place. It had to be exposed somehow. And usually that happens with landslides around here. So the only reason we're able to see all of these beautiful exposures of sediment now is because landslides and coastal processes like waves and things like that are eating away at the sediment on the coastline. This is a relatively small landslide. Oops. This is a relatively small landslide as a person for scale here. It's not tiny, but it's still pretty small compared to some of the others that we see. For example, this is the Ledgewood landslide on Whidbey Island in 2013. So this is it's actually that same Professor Swanson here, and a student examining this landslide. For scale, that's a house up on top of that, on the top of the landslide there. So this is a huge, huge, huge piece of land that has just slid away and exposed all of these glacial deposits. Another example of these long periods of boredom and short periods of terror is this bedrock here. This is a formation in Manchester State Park on near Bremerton. And these are rocks that formed on the seafloor tens of millions of years ago. And they tell an interesting story about the history of what was happening off the coast, 40 million years ago or so. But the only reason we're able to see these rocks, because they used to be underwater, and then they were buried and buried some more and buried some more. We're only able to see these rocks because of earthquakes and geologic faults, which have brought these rocks back to the surface where we can see them. I don't know if you know, it doesn't get as much attention as the big Cascadia subduction zone offshore that makes giant earthquakes, but there's a fault zone that runs right through Seattle, West Seattle and South Seattle, called the Seattle Fault Zone. We don't have, all of these lines represent either known or suspected locations of fault lines in this fault zone. There aren't very many places where this fault is actually visible at the surface, so we have to use some other methods to figure out exactly where it is. But there's a few strands of it. It basically runs from the Kitsap Peninsula, across Bainbridge Island, across West Seattle and downtown Seattle, out towards Issaquah, the east side, and then kind of blends in with a mess of other faults that are happening in the mountains there. There's some really beautiful exposures of that bedrock that are along this fault, which is really cool. There aren't very many places in Seattle where you can actually see bedrock, but some of the only places I'm aware of are right along here in Alki, where they've been exposed by this fault, and near Seward Park. There's a few exposures there, and then I believe there's a couple more out by Issaquah. There might be more in this area, but I'm not quite sure actually. It's probably buried by a lot of development at this point. So, like I said, there's only a few places where you can see bedrock around here because most of our landforms in this area, most of the entire surface of Seattle and the greater Puget Sound is covered by glacial stuff. So this is not quite in the Puget Sound. This is Easton Glacier at Mount Baker, but it's pretty representative of, on a smaller scale, the processes that have shaped the landscape that we have in the Puget Sound. So most of what we have around here are glacial deposits. As glaciers move across the landscape, they carry all kinds of sediment with them. They can pick up really big rocks, really tiny sand, a huge range of sizes, and just carry them in that ice until they drop them off somewhere else. And so we often see, you might be familiar with this if you've dug around in your garden or your backyard, or just looked at maybe a cut of rock in a construction site. There's this big mix of sediment sizes. You can kind of see it here. There's a lot of smaller stuff, kind of sandy sized sediment, and then there's these bigger boulders in there. This is on the right, another outcrop at Manchester State Park near Bremerton. This is one big stack of stuff that was deposited in kind of right on the edge of a glacier, kind of a glacial lake, and that's me for scale. I was pretty excited about seeing that deposit. Sometimes these deposits, instead of being all mixed up like this, they might be laid down in really nice, consistent layers. This is at Discovery Park. Sometimes when the tide is low, you can access this really beautiful stretch of sediment. We call this a rhythmite because these layers have been laid down in some kind of rhythmic pattern. Usually, if those layers are laid down like one layer per year, we would call that a varve. But if we don't know how often these layers are laid down, we just know that they're laid down at some kind of regular interval, then we call them a rhythmite. So this is a class of students at the University of Washington. They're taking a glacier class and they're out there.
Hey, Taryn. Your
Taryn,
microphone is not on. Ooh, I think her hearing or the headphones went out too. Hold on. Thanks for your patience with technical difficulties. She is in the zone. She's doing great. Taryn. We still can't hear you. Cool. Hey, Taryn. We can't hear you. We haven't been able to hear you for I don't think you can hear me. Yes, thank you, Claudia. Mm-mm. Taryn, I can try to take you out of the meeting and then have you come back in. Thanks again, everyone, for your patience. Okay. Yeah, we can try. We can try closing out and having everyone come back. I'm not sure. I don't think, can somebody else unmute and say something so I can make sure that it's.
So does someone have
Testing,
phone number?
testing.
I think it might be local to her.
I think so
Yeah,
too.
I can hear everyone else.
I don't know if closing the meeting will do
Yeah.
much.
Does anyone have her phone number that they can call her and let her know?
She knows.
She knows.
Can you hear me now?
Yes.
Yes,
Yay,
yay.
okay. I don't know why it kept muting me and my microphone on my headphones has stopped working, but I will go back to that. Sorry about that, y'all.
Cool. So
Yeah,
just so you know,
so it
I
looks
was
like my sound went out at the beach slide at Discovery Park, so I will go back there.
Yeah, you
Awesome.
were locked in with that. You were.
Yeah,
Find
it
my
was
slide.
impressive. And also, I was muting you to try
So
to.
many windows.
I'm muting.
Okay, back to you, Taryn. That was just an intermission.
Okay, great. This is where we were. Excellent. Thank you so much. Okay, so I was saying we have a class. This is a class of students at the University of Washington that was learning about glaciers. And so they went to this site at Discovery Park to look at these beautiful layers of glacial sediment that was laid down at regular intervals. And if we know that those intervals were yearly, then we would call them a varve. But if we don't know how often the sediment was laid down, then we would call it a rhythmite, which just indicates that it was laid down at some sort of rhythmic pattern, rhythmic interval. Another feature that we often see around the Puget Sound is called an erratic. These are giant boulders that were laid down by a glacier somewhere far from where they were originally grabbed. So the glacier would pick up a rock, say up near Bellingham, and carry it for tens of miles and then drop it down around here in Lake Washington. So this particular erratic is a, oh dear. So this particular erratic is in front of a house on Lake Washington. One of my professors pointed it out to me or told me where to find it, and it's just huge. They're not all this big. There are a few really big ones like this that I know about, but a lot of them are more the size of maybe like a few basketballs, and you can find them around just because we don't really have any bedrock cropping out in Seattle. Most of the big rocks that we see are carried here by glaciers from somewhere. So if you see a big rock sitting around, well, really, if you see most any rocks sitting around, they were probably carried here by glaciers. Another feature that you don't see in the lower Puget Sound as much, but you might see if you're out hiking or driving through the mountains, is a moraine. A moraine is formed when a glacier is flowing down a valley and it's pushing sediment out of the way and picking up and carrying sediment and dropping it on its sides or at the front of the glacier. And it builds up these big ridges at the front or at the sides of the glacier that we call a moraine. So this is a lateral moraine that was formed on the side of the Easton Glacier at Mount Baker. So the glacier was flowing down this valley here where my laser is. You can see the other moraine on the other side of where the glacier was over here. And you can see it's got these really steep sides because this is a pretty young moraine. It has not had a lot of time to erode away. It's got these big steep sides. There's a real skinny little hiking trail along the top of it. They're really, really beautiful features. One that we're more likely to see around the Puget Sound is a drumlin. So drumlins are these glacial features that are formed beneath a glacier as the glacier is flowing over the landscape. There's water that can flow beneath these ice sheets, and it'll carve away these features or deposit sediment to shape these features that are called drumlins. They're basically these like long, linear, sometimes we call them like a fluted feature. So they're just these long kind of rounded hills on the landscape, which you're probably really familiar with if you've walked around or driven around Seattle at all. It's a very hilly city. They're all drumlins. They're all dropped there by glaciers. Thanks, glaciers, for making it really hilly here. Here's a couple of, these are LiDAR images. LiDAR is a kind of measurement technique that we use to measure how landscapes are shaped. So we shoot lasers at a landscape, and when those lasers bounce back to our detector, we can get a sense of the elevation of those features. So on the bottom left, we have a LiDAR image of West Seattle looking south. So this is showing us in really nice detail the shape of the topography in West Seattle, where all of those hills are. And then in the top right, we have another one of North Seattle looking west. And you can see again, these really lovely linear rounded features that are basically going from north to south, because the big ice sheet that came here was also going from north to south, carving out these features. Another really common feature that we see around here are these finger lakes and fjords. Again, they're these really long linear features that are carved out by this ice sheet that was flowing down like this through the Puget Sound area. So we've got, of course, the main Puget Sound itself, a really long skinny feature. We've got Hood Canal, another long skinny feature, Lake Washington, Lake Sammamish. All of these features were carved out by water flowing under this big ice sheet that came down over the Puget Sound several times in the last couple million years. Another feature that's a little harder to find because you need a big chunk of rock, but you can find them around here and also up in the mountains, are striations. And striations are formed when a glacier picks up little rocks and drags them over other rocks and leaves these big scratches behind. So you can see them, I've outlined a few in this image. They're just all of these long scrapes on these rocks. Sometimes they're bigger grooves, maybe like kind of yay sized. They're very cool. I also love finding these when I'm out hiking, just because it's an indicator that there is actually a glacier sitting on this rock at some point that I'm now just hiking over. So I want to take a few minutes to discuss, just give us a break from me talking on Zoom. If a few people want to unmute and pipe in with places that you've seen some of these features, I'd love to hear about it. Maybe a favorite place that you've seen these around Seattle or the Puget Sound. And hopefully tech issues are sorted out, so a few people can unmute and do that. Oops. I'm gonna pause this.
I would say for me,
Can I see my participants?
was I supposed to raise my hand?
I think David is trying to say something, Taryn.
Was I supposed to raise my hand? I'm sorry.
No, it's okay.
It's just funny because a lot of the hilliness and things, I think, I know I erroneously attributed to
I think one person is
tectonic.
I'm gonna mute Taryn. Go for it.
I just had erroneously assumed that a lot of this was just due largely to like the tectonic activity in the plates, and it's really interesting to realize how much of the signature terrain here was actually created by glaciers, as opposed to what people like me would erroneously assume was just done by tectonic activity and things like that. So it was very enlightening. So thank you for that.
Awesome. Taryn, did you hear that?
Bree, if there's audio happening, I am not able to hear it on my end.
Yeah, I got you. I'm just gonna, so just so everyone's aware, I'm just gonna type into the meeting what David said. Did anybody else, and I'll just annotate everything that's being said audio-wise for
I
Taryn.
heard David.
Yeah,
I think Taryn is in a bubble of some kind.
Yeah.
Yeah. I haven't seen that much on the west side, but on the east side, certainly, on the Columbia Gorge and in Dry Falls State Park are just like massively like easy to observe. It'd be cool if somebody could produce like a little map that, just amateur folks that wanted to go out and look at them on this side could visit those spots.
I can probably get our 5th graders to do that. That's great.
That'd be awesome. Thanks.
Yeah.
Just if anyone wants a quick day drive to see really cool glacial geology, Mount Erie up by Anacortes. If you drive up to the top of Mount Erie, you can see striations really well, and it's a pretty cool place to go.
Really. Yeah, and so thank you for sharing. And I thought it was really interesting. I feel like people all over always think, or very commonly think, that because of our fault activity and the fault lines around here is why it's so hilly, whereas like the reality is it's just like this massive pressure from the glaciers that like create all of those different geological features, because the glaciers like formed and then retreated with the warming and then back and forth so many times that's like how we have so many cool, awesome geology features around here. Okay, so Taryn said, oh yes, tectonics do create hills in other areas like San Francisco, but around here it's all glacial. She also apologized for her audio issues. And then I know that at least our organization and at least some people are in West Seattle. And so I thought it was cool that we're one of the only places that can see bedrock here. And I think for whoever asked where exactly it is, I think somebody gave an answer that if you like head over from Alki Beach to the lighthouse is where you can see it. Does anybody have any info on where exactly that is?
I have a question for Taryn, please. So I know she probably can't hear us, but maybe it could be typed out. But just, when I was hiking around Mount St. Helens, they have these things called hummocks, which are these kind of like rolly, hilly things created by the flow from the volcano erupting historically and recently. But like, so how do they tell the difference between, how do they know when a hilly area is shaped by glacial flow versus like something intervening since then or contemporaneously, like a volcanic activity, lava flow or something?
Cool. So I just typed that out. I said, I don't know how to spell hummocks, so I just said Mount St. Helens hummocks from lava flow. How do you tell the difference from hilly areas shaped by glacial flows versus volcanic activity? And so Taryn just hopped out and she's coming back in.
I can hear you again. Oh, finally. I'm so sorry about this, everyone. That's never happened with my headphones before.
It's okay. Yeah. 2020 is the era of tech issues, and everything is slower, I think, than it ever has been, except for something. So somebody had a question about their experience with lava flow. They called them hummocks at Mount St. Helens, and they wanted to know the difference. How do you tell the difference from like hilly areas that have been shaped by glacial flows versus volcanic activity?
Yeah, so is this the hummocks trail near Johnston Ridge at Mount St. Helens? Because I think,
That's
if I'm remembering correctly, okay, great. I think those are actually They're from the landslide that happened during the Mount St. Helens eruption. So when Mount St. Helens erupted, it kind of blasted out the north side of it, and there was this giant landslide, and the volcano like blasted out the north side, and all of the big chunks of entire mountainside from that landslide kind of ended up over by Johnston Ridge, and that is the Hummocks Trail. And then lava flows, there's more lava flows on the south side of the mountain, and they do, if you see them from above, you can kind of see that they make some hilly shapes too. How you would tell the difference between those and glacial deposits, with no context, it would actually be kind of hard, because the deposits that you get in a landslide tend to be just a big mix of different sediment sizes, just everything that was all jumbled up in that mountainside. And they might all be kind of like angular and broken up. And you see something fairly similar in that glacial till, the stuff that's laid down by glaciers. Differences that I might look for, if it was a glacial deposit, then some of the rocks that are in that jumbled up mess would be likely to have those glacial striations on them, the little grooves that are carved by rocks rubbing against each other. And I might also look for presence of like organic material. If there's a lot more just bits of tree and stuff like that in the deposit, then it might be more likely to be a landslide. But if it's a glacial deposit, just because the environment that the glacier's in is so much colder and like has a lot less stuff in it, organic stuff in it, there might be less of that in a glacial deposit. Ooh, Francisco says, how can we differentiate tectonic from glacial striation? Probably context. Glacial striations you would see on, if you have like a big piece of rock that's sticking out of the ground and it's been, has a glacier flowing over it, it would be smooth. Tectonic striations can kind of be a lot of different orientations. But there's probably a better way to tell them apart, and I can't think of it off the top of my head.
No, because I was thinking about the different angles that the tectonics can bring the striations, but they can also be horizontal. So if you came across that, if you don't know the geological history of the place, I don't know if one could also quite actually know the difference.
Yeah, I think like knowing the context of what you're looking at really helps a lot. And so you're usually gathering clues from a lot of different places to kind of figure out, oh, like there's a lot of things around here that suggest this is glacial, so it's probably glacial. But you could have both. Looks like John said radial distribution versus north-south lineaments. Yeah, the direction is going to totally depend on where you are, because you can have glacial striations going east-west up in the mountains. If you have just smaller glaciers flowing west down a mountainside or something. But if you look at striations in a whole bunch of different places, like if we looked at striations all around the Puget Sound, we saw they're all kind of going north-south. Like, oh, that's probably because there was a giant block of ice that was sliding from north to south through the Puget Sound. We will definitely have more time for questions at the end. Maybe I'll keep moving into the paleoecology section now that hopefully all of the tech is working again, fingers crossed. Get this sharing again. Hold on. Come on, PowerPoint. Okay, share screen. Great, okay. So moving on to paleoecology. So in a nutshell, this is the study of ancient organisms and how they're interacting with their environment, how they're interacting with each other, and how that's changing over time. So essentially, we're trying to answer the question of how do we reconstruct a scene like this? All of those cool murals that we see in museums and textbooks and stuff like that, where is that information coming from and how are we figuring it out? So to answer this, I first want to do a little crash course in sedimentary geology. So you might remember the rock cycle from middle school. We've got our igneous and our metamorphic and sedimentary rocks, and they all kind of interact with each other to form each other. But we're just going to focus on sedimentary rocks because igneous and metamorphic rocks don't really tell us a whole lot about the environment because they form really deep in the earth where it's really hot and things don't live. So sedimentary rocks are formed, most sedimentary rocks are formed by the transport of sediment from one location to another. The most common ways that sediment is transported is that it is carried in water, it is carried by wind, or it is carried somewhere by ice. The size of the sediment that we see in different locations is going to depend on the energy with which it was transported. So if you have a really high energy environment, think like really energetic, it can carry really heavy stuff. All of the small stuff is just going to be totally whipped away out of there. And you're going to be left with just the really, really big rocks that are so big that like even the most energetic environment can't lift them. If you have a medium energy environment, then, well, there wasn't enough energy to get the big rocks there, but there's enough energy to get rid of the small rocks. So all you're left with are just kind of the medium-sized rocks. And if you have a very low energy environment, there wasn't enough energy to get all the big stuff there in the first place. And there's not really enough energy to even carry the small stuff anymore. So that's where you get your like mud puddles. There's also different kinds of sedimentary structures that we find in sedimentary rocks. And these are kind of like little bonus stories. So just looking at the sediment itself, we can learn something about the kind of energy of the environment that it was deposited in, or maybe the composition of the rocks that we see tells us something about where they came from. But these structures that we see tell us like little bonus stories about the environment. So for example, if we see mud cracks, let me get my laser back. So if we see mud cracks like here on the left, that tells us that that was an environment that not only was muddy, but also was able to get wet and then dry out and form cracks like we might see in a mud puddle after it's dried up after a week. If we see ripple marks like we have on the right, then that tells us that we were in some kind of environment where we had water that was flowing, maybe all flowing in one direction, maybe just kind of flowing back and forth, and making those little ripples in the sediment that you might see if you look in the sand at the edge of a lake. And also that those cracks or those ripple marks were able to be preserved. If we see bedding, which is these layers in sediment, then that tells us that we were in some kind of environment that was calm enough and regular enough to allow these layers of sediment to be laid down one after another over time. So that's all sediment, sedimentary geology. There's also fossils. So plant fossils will tell us something about the environment that they were in. So if we see a conifer, that might tell us that we are in an environment kind of like we have here, where we have lots of cedars and fir trees and spruce trees. But if we see something like a palm, maybe that was a more tropical environment. We don't really, like there are some weird houses around here that do have palm trees and like, I don't understand it, but there are houses with palm trees here, but for the most part, like they're not a natural part of our environment. So if you see a palm tree or a palm frond in a rock, and that tells you this was probably a more tropical environment where we would get a tree like that. If you see something like maybe a maple leaf, then that might tell you that this was a, often around here, we see maple trees in kind of the wetter lowlands, like by a river or something like that. So it might tell you you're in an environment, something like that. There's also, of course, animal fossils, which will tell you something about the environment as well. So a saber-toothed cat would tell you that the environment was whatever saber-toothed cats live in. There are a bunch of different kinds, so you kind of have to know which one you're looking at. But it also tells you that the environment was able to support enough prey to support a saber-toothed cat. And if there's enough prey for the saber-tooth, then there has to be enough vegetation for all of those, you know, mice or whatever to eat. If you find a clam, then that tells you it was some kind of watery environment, right? Clams don't live just like on the sides of trees. If you find a horse tooth, then you might be in like the grasslands or something where wild horses live, and so on. So we put together all of these clues, something about animals and the plant fossils that we see, and information from the sediment that we find and the structures that we see in the sediment. And we can use all of those clues to reconstruct an environment and say, okay, in this particular little area, I see clams and I see ripple marks and I see really, really small sediment that must have been in a really low energy environment. And all of those things are telling me I've got clams, I must be in water. I've got ripple marks, so I also probably must be in water. This must have been some kind of like a lake or near the like near a beach environment, something like that. So what I want to do is take another minute or 10 minutes for breakout rooms, and all of us are going to try and do some little super simple environment reconstructions and see if we can piece together clues. You all get to be geoscientists for a minute. And this isn't the type of geology that I do, but I really enjoy doing stuff like this just because it's like being a detective, but for rocks. So let's get some breakout rooms together.
Yeah, so I've got everybody, so if we have 6 rooms, it'll be 5 to 6 participants. And it might, because I am not able to make you a co-host, I can only transfer the host to you. It might
Okay.
One, so you know.
That's okay. So before we go there, I've got instructions and all of your clues for the rooms at this link. So I'm going to drop that in the chat as well. It's, if I can get to the chat. Got too many windows. I can't find my chat window.
I can put it in there.
Okay, thanks.
Would you like me to type?
bit.ly/DNDA1122.
It's not a hyperlink, but if you copy and paste it, it should work.
Mm-hmm.
Looks good.
So when y'all go into the breakout rooms, just note which breakout room you're in, which number. While you're in there, you'll have 10 minutes. Go ahead and introduce yourselves and just tell folks really quick your name and where you're from. And then pick one person to represent your group when we come back, because we'll discuss everyone's interpretations for a few minutes when we come back. So while you're in your breakout rooms, you'll have a set of clues, and the link is going to take you to a Google Doc that has the breakout room number and a name, and then the list of clues. And also the document is totally open, so y'all can write in it, write a bunch of notes, write your environment interpretation, whatever you want in there. Some questions to consider while you're learning to be a geologist really quick right now is, where would I find something like this if it's a fossil? Where would I find something like this animal or plant today? What would this eat, or what would eat this thing, and what does that tell me about the environment? Where did this thing live? Or if it's sediment, how did this sediment get here? Like, what was the energy of the environment? Or where might I see sediment like this today? If it's sand, maybe it's a beach, things like that. And then based on all of your clues, as a group, you can try and suggest an environment that they might represent. And this can be really simple. It can just be tropical beach or tundra or something like that. It doesn't have to be super, super detailed. That's fine. And then when we come back from breakout rooms, the representative for each group will just share what your group, what your clues were, and what environment you thought it was, and just a reason or two why you thought that was the environment. Okay. Are we ready to go to breakout rooms?
Yes, people are dropping like flies.
Okay.
In a breakout groups, so we'll do our best.
Okay.
Okay, see you all in there.
All right. Well,
sorcery.
Yeah. All right. Well, I will go ahead and keep going then. So our group representatives. So we ended up having 6 breakout groups, right? 5. Okay. So let's hear from, let's see, group 1 and 5 would have had the same set of clues. So can we hear from the reps for those 2 groups? What you thought your environment was?
This is Jenny from group 5. We were thinking that our environment was kind of like either like an estuary or a creek type of situation.
Okay. What were your clues?
I don't have them in front of me anymore. Clams, snails, small ripple marks, and mud type sedimentary, small sedimentary.
Okay, great. And so you thought it was like an estuary or a creek kind of thing?
Yeah, something with slow moving water.
Yeah, that sounds great. And then, sorry, you were 1 or 5?
5.
5. Okay, so then group 1, could we hear from you?
We forgot to actually make a rep, but my daughter would like to maybe rep for
Oh,
us.
fantastic.
We were probably thinking like an estuary or a bay because the clues were like rocks with ripples, and I was paying attention, and rocks with ripples apparently means that they have probably been underwater.
Mm-hmm.
So I was thinking like, you know, an estuary.
Yeah.
Or a bay or something, you know.
Yeah. And then the clams and snails.
Yeah, something with water.
Yeah, no, those are great ideas, and both groups are right. That is definitely a watery environment with clams and snails. Generally, well, snails you can find outside of water, but the clams tell you that it's probably a watery environment. The really small sediment also, and the ripples in the sediment tell you that it's probably water. So yeah, something like an estuary or a bay sounds really great. What about group 2?
Our speaker bailed out at the last second, so I guess I'll do it.
Okay.
So our clues were we had rocks made of medium small sediment like sand, fossil palm fronds, fossilized turtle, and rocks with thin layers and ripple marks. We did have an edge. We had one of your previous associates in our group who was tremendously helpful.
Wonderful.
And we came to the conclusion that this was some sort of like sandy, watery area just due to the fossilized turtle, the palm frond, the sediment like sand, and the ripple marks, which were indicative of some sort of water, moving water.
So a little bit of water, maybe not entirely water if we're getting turtles and palm fronds.
And turtles, yes.
Yeah,
turtles.
Exactly. Great. I just realized I was in group 3 and we forgot to pick her up. So I'm great at handling my breakout rooms. Would someone else from my group like to speak really quick?
I'll be happy to. We had sediment of different types. Animal was a mammoth, and petrified wood is spruce. We thought this was some type of cold environment, possibly glacier.
Excellent summary. And then group 4 was our last group. Do we still have anyone? Well, if not, then I can read group 4 off really quick. Okay, so group 4, the clues were some medium small sediment like sand and mud, a fossil salmon, a mysterious aluminum cylinder, and some petrified wood, but with nails in it. So maybe people can pipe in with a couple ideas really quick since we don't have anyone speaking from group 4.
Yes, sorry, that had a little tech problem also.
Oh, okay,
So,
sorry about that.
we were gonna co-present Claudia the first 2 clues and then me the second. And we believe that is a much more recent deposit because of the aluminum. It must probably from something human-made, some type of can. And the nails, well, also probably from petrified wood. I didn't know if the nails are iron nails, or you would say like human nails. That's something I didn't know.
Like iron nails, yeah.
Iron nails, okay. That I didn't know. So yes, to be petrified, it would have to be something.
Sorry, Francisco.
My friend, my colleague told me that probably was a delta because of the transition from ocean to river is very common from the salmon from its migratory travels to to breed. And the sand and medium sediment is also very common of the delta.
Excellent. Yeah, those are really great great details with like where the salmon are migrating and the kind of transition from sand to mud. So yeah, it sounds like everyone did a great job kind of figuring out what their environments were. I'll go on to the next slide really quick. So you might have noticed that all of the breakout rooms had names like Chuckanut and Blakeley and Vashon. So all of those clues that I gave you were actually different kinds of formations that we do see around the Puget Sound. So the Chuckanut Formation, that was the one that was kind of, that had the turtles and the palm fronds. So it was maybe a beach area, kind of in the water, kind of not. And that was a very old, like 40 or 50 million year old formation that existed in this area before even the Cascades and the Olympics were here. So before we had the mountains, and it was a much warmer, almost a subtropical environment where we had things like turtles and palm fronds. And nowadays we can see a little bit of it, mostly around Bellingham, and a little bit in the Mountain Loop area, a little bit on the San Juans. The next one, the Blakeley Formation, that was the group that had the clams and the snails and some ripple marks. And I think you said that it was an estuary type environment. There's a little bit around here. There's a little bit near Bremerton on the south end of Bainbridge. And that's also the one, it's not shown on this map, but that is the one that shows up near Alki. So that is a marine sedimentary rock. So it formed offshore, but very close to the shore. Some like 20 to 40 million years ago as the mountains were forming. And then the Vashon Formation, which is the one that had the mammoth tusk and the petrified spruce tree. That's all this glacial stuff that we've gotten that covers most of the Puget Sound that came in the last couple million years as we've had this big ice sheet advance and retreat over the Puget Sound. And the last one, the Duwamish with the aluminum can and the wood with nails in it, that's one that I kind of made up, but something that maybe a future geologist would see around here if they were looking at deposits in the Seattle area, which has obviously been very influenced by humans now. And there might be, human items in the sediment as well as the more organic, just sediment and animals that live there.
Taryn, do you need to be showing slides right now?
I do. Am I not showing slides right now? Let me reshare.
Oh, sorry.
Right. I forgot that goes away during breakout rooms. Thank you so much for checking that. Okay. So you can see this now. So what I was showing really quick was the, get the laser again. So the Chuckanut Formation is the orange here up by Bellingham and in the Mountain Loop area. The Blakeley is this orange kind of by Bainbridge and Bremerton, and then also near Alki. And then the Vashon is this yellow that covers most of the Puget Sound. So most places you are around here, if you're looking at rocks on the surface, it's part of the Vashon Formation, which is, I like to call it just a big pile of glacial junk. And I'm a glaciologist, I study glaciers, I love them, but it's just a big pile of glacial junk. So that leads into just the last part of our talk, which is about the broader geologic history of the Puget Sound. So first, again, our context, we have our subduction zone with one plate going under another tectonic plate off the coast of Washington. That pushed up the Olympic range and then also the Cascade range here. And the Puget Sound is just this little trough in between those two mountain ranges. And I actually I zoomed in on this image. This is the cover of a book. And there's a little tiny space needle there. So it actually is us. It's not even just a random diagram. It is actually us. So yeah, the Puget Sound initially formed, or at least the basin that is now the Puget Sound initially formed during this mountain building period several tens of millions of years ago. But the sound itself, this network that we know today of these deep troughs filled with water, was created by glaciers. So we had what was called the Cordilleran ice sheet. There were two very large ice sheets that covered basically all of Canada and flowed down into the northern parts of the US. There's the Laurentide, which is the really big one, covers most of Canada and came down over Minnesota, Wisconsin, Iowa, etc. Land of 10,000 lakes. It's because there was ice there. And then the Cordilleran ice sheet was the one on the west side of the Rockies that stretched from southern Alaska down to Washington. And you can see here, there was a lobe of the Cordilleran ice sheet, which we call the Puget lobe, that kind of came down from the kind of Victoria to Vancouver area and just filled in that basin that was between the Olympics and the Cascades. The lines here are showing the thickness of the ice. You can see over the Seattle area, it was like 3,300, 3,600 feet thick. So over half a mile thick, really a ton of ice. And that ice went as far south as Olympia and Tenino. So beyond that, no ice over those areas. And I could explain the history of glaciers coming in and leaving and coming in and leaving. It did that about 7 times in the last 2 million years. But this video from the Burke Museum really does a fantastic job of visualizing and explaining all of that. I'm going to drop this link in the chat so that people can watch it, because I think if I try and just share it on my screen, it's going to be really laggy for folks. So, oh, come on. I'm going to drop that link in the chat and give people a few minutes to, give people a few minutes to watch it, and then we can come back and finish this up. And I'll summarize it real quick at the end for those who don't watch it. Okay, so I really like that animation. I think it does a fantastic
Can anyone else hear?
No.
Taryn, can you hear us? Last time it worked when she just hopped out and came back in. She says that she only has one more slide. Do you, she can't hear us.
Can people hear me? Can people hear me? Oh, maybe.
I can.
I can too.
So Taryn left and I think she'll be right back. Hopefully. There she is.
Okay, I don't know what keeps happening to my audio, but I'm almost done, so that's okay.
We're gonna make it.
Gonna make it. Okay. I'm not even going to start the presentation mode. I'm just going to talk about that video that we just watched, which I think is very cool. It does a fantastic job of summarizing and just visualizing the last 20,000 years in the Puget Sound. So essentially what we saw there was that there didn't used to be a Puget Sound. It was all pretty much land. Glacier, the Puget Lobe came in. That's actually one of about 7 times that we had glaciers come in and out of the area, but it carved out all of those big, long lakes and the Puget Sound itself, all of these long water bodies that we see now. After it left, which was about 12 to 14,000 years ago, we weren't done yet. You might have noticed that West Seattle, that whole area was actually a separate island. It was not attached to the rest of the Seattle, South Seattle area. That was slowly filled in, well, not super slowly, but it was filled in about 5,000 years ago. There was a lahar from Mount Rainier. A lahar is like a volcanic mud flow, and this was a very, very huge mud flow that came off of Mount Rainier and flowed down those river valleys and filled in a lot of what was an open saltwater area and connected West Seattle to the rest of Seattle. So I know a lot of you probably feel like you're a bit of an island right now with the transportation issues getting to the rest of Seattle. You used to actually be an island. I don't know if that makes you feel any better, but kind of interesting. And then of course, nowadays we've made further human modifications to the landscape around there, like building Harbor Island. So, but as you could see, a lot of that, a lot of what we see now is carved out by glaciers. And I just wanted to end with, we have glaciers to thank for all of our hills. And this is an elevation profile across West Seattle, roughly along Alaska Street, running west to east. And you can see that there's these big hills and troughs and another big hill, trough and hill and trough, and you have to go up and down and up and down. That's all thanks to glaciers. So with that, I guess we can move on and take questions and discuss. I'll stop sharing my screen.
And thanks for the explanation of why biking here is so difficult.
Biking's hard. We have like not very many east-west streets that are functional. It's great. I love it though. Sometimes I count them if I have to drive really far west to east, like from Ballard to UW or something. It's like 1, 2, 3. I think there's 7.
Yeah, I've heard that too. Does anybody have any questions?
So I noticed the big dip in the elevation east to west, where I guess I'm assuming is what Delridge is. Is that anything in particular that caused that, or is it just glaciers quote unquote.
Glaciers. Yeah, I don't know exactly what causes the variability between like some of the hills are a little bit higher than others or dig a little deeper than others. I have been meaning to measure this, but I'm pretty convinced that near where I live, like the west sides of the hills are not as steep as the east sides. Don't know why, but kind of interesting. But yeah, there's just little variabilities beneath the glacier.
Did you see this question that Kelly posted in the chat?
Yes, predictions for the geologic future of the Puget Sound area. I think the first thing that comes to mind is that, so I mentioned that Seattle fault earlier. I think we can expect to see earthquakes from there again, not to scare folks, but I think we get quakes there around every maybe 1,000 years or so, a few thousand years. They're not all necessarily gigantic. They're not a magnitude 9, but because that fault is very close to the surface, that is a bit more of a problem for Seattle, just because we've urbanized so much right over that fault. There's also the Cascadia subduction zone that's offshore that would could create a magnitude 9 earthquake. We're far enough inland that the shaking would be bad, but it wouldn't be absolutely catastrophic like if you were very close to it. There would be tsunamis on the coast, but it would have to be a very, very, very particular configuration to get a tsunami to go like around the Olympic Peninsula and into the Sound. Glacier-wise, the way things are going, I don't think we're going to see another glaciation anytime soon. Let's see, Joe says, I'd heard that drumlins tend to be steep towards the origin of glacier flow and taper in the direction of flow. Is that correct? I believe so. I flip them around sometimes, but I believe that they are steep. Wait. That might be a different feature. That might be Ruche Montagnais, which are steep. The glaciers flowing this way, they're steep here and then shallow off this way. And then I think drumlins are the other way, that they're shallow in the direction of flow and then they kind of steepen off on the other side. But you might be right. I might be flipping them. What I was thinking about with the one side being steeper than the other is if the glacier's flowing this way and making something like this, I was talking about like the kind of in and out of the screen, if this makes sense, that if I'm standing on the drumlin and it's like long and linear away from me, then like to either side of me, one side is a little bit steeper than the other. And I've just been curious about that and meaning to measure it for a while, because when I go for walks, one direction of my walk seems to be steeper than the other.
I have another question. Sure. Obviously, the glaciers in like Mount Rainier are reducing and decreasing, but I'm wondering what are are there biological impacts to that you can like talk about? Or
yeah, absolutely, yeah. And I really didn't talk a whole lot about more of like my expertise, which is specifically on modern glaciers and how they're changing, but there are a lot of biological impacts to glacier loss. So one that that I usually bring up when I give more of like my research talks is salmon are really influenced by stream temperature. If the stream is too warm, then they just can't survive. And so around here, glaciers are really important in the summer and fall as they're melting, which is normal that they get snow in the winter, they melt a bit in the summer and fall. That happens. That meltwater helps keep stream temperatures cooler. And also because we have such a dry summer climate, most of the water that is in some of our rivers in the summer and early fall is coming from glacier and snow melt because there just isn't that much rainfall. So if we didn't have them, then our stream temperatures would be much higher and there just wouldn't be that much water in the streams, and that would be very bad for salmon. I know, so I had a summer internship with Kenai Fjords National Park in Alaska, and I was studying glacier change there and talked with some folks about how a lot of different animals up there really rely on glaciers as part of their habitat. So there's some birds that like basically do all of their fishing like at the front of glaciers. Harbor seals like to haul out on little glacial icebergs. That's where they hang out when they're not in the water. There's a lot of animals that really do depend on glacier environments as part of their habitat and their ecosystem. I see in the chat, Claudia asked, is there a website with a map or list of places in the area with GPS coordinates that pinpoint where you can see the features in the photos I showed? I do not have a map. So most of those photos were just my photos from like field trips that I've gone on over the years, and I don't have a map that shows that, but there is an app called Rocked, R-O-C-K-D. I'll drop that in the chat. This is a kind of a crowdsourced app. So they use another website that compiles geologic maps like across the world. So when you open this app, you can get a geologic map of wherever you are. And then what Rocked does on top of that is users can like check in at different locations and show like pictures of what they're looking at and include information about like, I saw this fossil or it was this rock type. And then when you go and look at the app, you can see all of the different places that people have checked in publicly. And so then you can go to those sites and see what other people have logged. I think that would be the best aggregate that I can think of to just kind of find stuff around here. There's also, I'll drop a couple more things in the chat. David Williams is a local author who's published a couple of books about the geology of like Seattle and the Puget Sound. I think he has like a Seattle Geology Walks book or something, and also just some cool natural history. I want to say he has a book about how we like erased an entire hill from the Seattle landscape because it was in the way. There used to be a Denny Hill. And there's also just some blogs. I think there's like a Reading the Washington Landscape or something like that blog that does things like that. And oh, there was one more I was thinking of. Roadside Geology of Washington. And I'm sorry, I'm getting more into books rather than just like a website with GPS coordinates. But the Roadside Geology of Washington, specifically the second edition, it's more than just the Puget Sound, it's all over the state, but it's a fantastic resource for just learning about what it is that you're seeing as you're driving around. It has like mile markers and extensive descriptions of different outcrops that you see on the road. Yes, thank you, Mary Alice. Too High, Too Steep by David Williams is about the Denny regrade and other alterations to our landscape. And I also see a question from Jen, if there's a program that combines geology with hiking. Yes, I have two answers to that. One, I've been wanting to start something like that for a very long time. So feel free to reach out to me if you're interested in talking more. I also know that Mountain Madness is a climbing company they're based out of West Seattle, and they do guided climbs and guided hikes around the Cascades. And I'm going to be working with them next year to start doing a guided glacier tour where you don't have to have any kind of like glacier travel experience, but basically go out with an expert scientist who's me and talk about glaciers and the geology of the Mount Baker area and how that has shaped the landscape. So add that in the chat. Yeah, you should check it out. It'll be really fun. I'm excited. Oh, I forgot I was going to put a slide with a couple of resources at the end, but there's a professor at Central Washington University named Nick Zentner. He has a YouTube channel and a PBS show called Nick on the Rocks. He does a ton of just really fantastic short geology videos. I binged his PBS show earlier during COVID. Nick Zentner is my hero. Yes, he's fantastic. He's hilarious. He started just like doing live streams during COVID. I think I got the impression that he was just like driving across I-90 one day and was like, I should live stream this. So if you want to just learn about little snippets of cool regional geology, it's great. And also Terry Swanson is the UW professor that I mentioned a couple times. And he is streaming his 101 geology lectures on Twitch. So those are public. You can just go watch his fantastic intro to geology lectures on Twitch if you'd like. I think that they're recorded, so you don't have to watch them live if you're not free at like 10:30 or whenever his class is. I just dumped a bunch of resources, but yeah, do people have other questions for me? And feel free to put them in the chat or just unmute yourself.
And so everyone knows, I'll follow up in an email with all these resources.
Awesome, thank you.
And your contact info, if that's okay.
Yes, yeah, I can put that on the chat too. Are people excited to go out and find an erratic or bike over all of the drumlins or anything?
Yeah, I just want to say this was really, really, really good. And,
thank you so much.
You did a wonderful job. Really appreciate this. This is super informative. So yeah.
Well, thank you. I'm glad you found it helpful, even despite all of the tech issues.
Well, I mean, I'm not a geologist, but at the same time, it's still fascinating to know the rocks that are beneath your feet.
Yeah, no, I love it. I love it. Even though I study ice as my main gig, I really enjoy just learning and thinking about what else is going on around us.
Yep. So no return of the glaciers anytime soon. They're not.
Probably not.
They're not going to swing back around.
They're not on a good track. Yeah, my primary research is I use satellite images to study glaciers in Greenland and Alaska and measure how they're changing over time, and they're mostly getting smaller.
I saw you talking about LiDAR. We used that back in one of my past lives. Use that a lot. It's really fascinating what that technology can do.
Oh yeah.
Because it can get into the cracks and behind things, around corners and stuff like that. So
yeah, it's really cool.
I just want to mention that I put a link in the chat, and that is for a post-workshop survey, which might just like make everyone yawn. But it's really, really helpful for our grant reporting to get some feedback. So I'll just put it in the chat 3 more times, just in case you didn't notice it. And like I said, I'll follow up in an email with all the resources that Taryn put. We're gonna make this video, well, it's a Zoom meeting, but we'll make it available online to be able to review. I'll hopefully edit out some of the tech issues. But yeah, I'll send that out in an email also. And if there's any questions, like please feel free to ask.
Yeah, I'll stick around for a bit if folks are shy.
Otherwise, I just want to say thank you so much for coming out to one of the wetland workshops. And we have another one on December 13th on the future of restoration practices in a warming climate. So yeah, and just stay tuned to DNDA if you're interested in that.
Awesome. Thank you, Bree.
Thanks, Taryn. And thanks for tuning in from so far away.
Thank you.
In
Bulgaria.
Gracias.
De nada.
Gracias, de verdad.
That's my grandma, the other person on the video.
Oh, oh yeah, I see the last name. I saw one of my friends called called in from London.
Can I ask you a question, Taryn?
Absolutely.
That's kind of, are you still here?
I'm sorry, your audio cut out a bit there.
Oh, cool. So it's so off air with it, but oh gosh, I'm having so many tech problems today too. It's really annoying. I've lost connectivity like 10 times. Can you guys hear me still, or
yeah,
I can always email it.
Yeah, we can.
Frustrating.
We can hear you.
Oh, cool. Oh, okay, cool. So what I wanted to ask about was, it's so kind of off the main the Salish Sea area, Puget Sound, and originally, but of course some of those hills were like mowed down and flattened in order to do this urban development that they did. But they said, they said the other famous city that has 7 hills is Rome, and that always kind of stuck in my head for some reason. I don't know why, but I'm just kind of curious. It's like, other parts of the world where you see similar features, are we to sort of assume they were also under an ice sheet millions of years ago? Or can, features that look apparently really similar, kind of, I guess, going back to the hummocks thing, I guess a little bit, but like they look somewhat similar, but they can be coming from really divergent, like, origin stories?
Yeah, I think it's a bit of both. So if you're just thinking like just that there's hills or there's some hummocks, then yeah, we're going to see that in a lot of different places. I think one of the distinctive features with ours is that they're all these long linear hills. They all run from north to south. They're not a mound so much as like a very long kind of a pencil-like feature. And so we do see those in other places in the world, Canada, Scandinavian countries. So in those places, it definitely is indicative of there were also glaciers here. You can also get, including long linear hills, you can get those from other processes. So like tectonics, faulting, pushing things up, those will tend to have some other kind of geologic clues that we might notice as well. Especially like those, something like that that's from tectonics would actually be made of bedrock rather than just like these drumlins are just literally just giant piles of sediment. So there's some differences like that. So yeah, I guess that's one of the fun things about being a geologist, in my opinion, is like having to puzzle out all of those different little clues. It's like, okay, well, all of these cities are hilly, but they probably weren't all glaciated, right? Like Rome probably wasn't glaciated. It's, pretty far south. It was probably a little warmer than we were 20,000 years ago. So what was driving that? And I don't know specifically the geologic history around Rome, but like San Francisco came up earlier, and that's more tectonic and earthquake related, why they are so hilly. I hope that was a clear answer.
Great.
Any other questions?
I'm feeling people might be lingering without realizing it.
Possibly, yeah. Definitely spaced out at the end of a seminar or two, and oh, I need to end this.
Yeah. Well, if there's no more questions,
Hi guys.
you can go for it, Adam. Oh, see ya.
Okay.
If there's no more questions, do you, Taryn, want to jump on the other Zoom link from earlier?
Yeah, sure. Can do that. All right, see you in a sec.
Okay, thanks.
Thanks.